Hello students, topic 23 is a review on matrices and related ideas. A matrix is a rectangular array of objects. The dimensions of a matrix are expressed as the number of rows by the number of columns. The entry in the ith row and jth column is represented by a sub ij, and the first non-zero entry in a row is called a leading entry. Now, given the matrix below, identify its dimensions and the leading entry. So the dimensions of this matrix has 2 rows and 3 columns, therefore it is a 2 by 3. Because there are 2 rows, there are going to be 2 leading entries. Each row has its own leading entry. So look at the first row right here. The first non-zero, looking at the row left to right, is that -5. So let's call this the row 1 LE, stands for leading entry. And it's in the first row, first column. So this notation would be a sub 1, 1. Don't read that as a sub 11. Read that as a sub 1, 1, meaning first row, first column. If you do have multiple digits, double digits, as far as number of rows and columns, and you wanted to say the 11th row and 12th column, then use a comma to make it more clear. But if you just see a single, if this looks like an 11, read that as a 1, 1. And that entry, of course, is that -5 that we see there. And then the row 2 leading entry, looking at row 2, the first non-zero entry is that 2. And that's in the second row, second column. So we would say this is second row, second column. Again, don't read that as 22. It's 2, 2. And the entry is 2. Now, a column vector is a n by 1 matrix. In other words, it's a matrix with 1 column only. And a row vector is a 1 by m matrix, which means it's a matrix with 1 row only. Give an example of each. So let's do a 3 by 1 column vector. And just 1 column, but let's do 3 rows. 6, 0, 2 will be my example for that. And then let's do a 4 by 1 row vector as an example. So oops, I wrote that wrong. That should be a 1 by 4. 1 row, 4 columns, and here's our row vector. And any numbers here. You can even put variables. You can put x squared as an entry, 7. So this would be an example of a 1 by 4 row vector. Now a scalar is a 1 by 1 matrix. So 6, you don't need to put the matrix in brackets if you're referring to a scalar. You can just leave it outside of brackets. So just in other words, any single number we refer to as a scalar. So several examples. Scalars can be also functions that represent numbers, irrational number, pi, etc. These are all different examples of scalars, 1 by 1 or 1 by 1 matrices. Okay, next slide. A row operation on a matrix is any of the following actions. Multiply all entries in a row by non-zero constant. Interchange any 2 rows, or replace a row by adding a multiple of another row to it. Alter the matrix below by performing each row operation at least once in any order, but in succession. Now there are a variety of notations for indicating which row operation you're doing, so that when you do a row operation and change the matrix, you can have notes communicating to the reader what the row operation was. And so in this case here, I'm going to do any row operation. In any order. Let's just go in order, 1, 2, 3. We're going to begin by multiplying all entries in a row by a non-zero constant. So let's multiply every single entry in this row here by 2. So that gives me, a new top row, -10, -8, 24, and then I'm going to leave the other 2 rows unaltered. Normally you just do 1 row operation per change, otherwise it can be quite confusing as to all the different things that were done. Now next, underneath this equal sign, you can indicate using some sort of notation what the row operation was. And what I typically do, well, there's a variety of things that I've done in the past, but one that you'll see that's pretty common is to, underneath this equal sign, is to write down something like this, 2 times row 1, 2 times r sub 1. And that indicates what was done to produce the new matrix. And I shouldn't put an equal sign there. These matrices are not considered to be equal, but an arrow would be appropriate. If you double row 1, then you get this new matrix. Okay, we're going to do these row operations in succession. So let's do another one. Second row operation is interchange any two rows. And so to indicate that I'm going to interchange two rows, I do something like this, R2, double arrow like this, R3. This means I'm switching rows 2 and 3. And I'm going to use this as my starting place. So the first row we left unchanged, so I'll just leave that. But then we interchange rows 3 and 2. So row 3 is now row 2, and row 2 is now row 3. And then finally, we can do the third row operation, replace a row by adding a multiple of another row to it. For example, suppose I wanted to make that 0 by adding double 5 to it. I'm going to double 5 and then add that to negative 10. So here's how I'm going to indicate doing this row operation. I'm going to double row 3 and add it to row 1 to produce a new row 1. So this is the row operation of replacing a row by adding a multiple of another row to it. And we wind up getting the following. Now this work is done mostly in your head. You don't need to write this all down, but you're going to double every entry in this third row, hold that number in your head, and then add it to this row to replace that row. So in other words, I'm not looking to change rows 2. So let me rewrite row 2 or row 3. Those are not intended to be changed by this row operation. Now I'm going to do the calculations. So I'm going to double this 5, makes it 10, add it to negative 10. That zeroes out. I'm going to double this 10, which is 20, and add it to negative 8, and that gives me 12. And then I'm going to double this 0, which is still 0, and add it to 24, and that stays 24. So here's the result of doing this particular row operation. Now I do have some other notations that I have used before to get these results that differs from this notation. This kind of notation is very common in the literature. You'll see this in textbooks quite a bit. But also I like to keep things simple, so what I'll just do is I'll put a 2 outside this first row, and that's an indication to me that I just doubled everything in that row. A really easy way to indicate that. If I want to interchange two rows, then I say, okay, well now I'm going to interchange rows 2 and 3. So I just do a double-sided arrow like this. And then if I want to do the third row operation, which is double row 3 and add it to row 1, what I do typically with that is I put a 2 in some parentheses outside row 3 with an arrow pointing at row 1. So this is an indication I'm going to double everything in this bottom row but add it to the top row to change it. So this notation here tells me I'm changing the top row, not changing the bottom 2 rows. So like the doubling of the third row is a temporary doubling. Notice that it doesn't stay doubled. Right, the whole purpose of this third row operation was to change the first row. And I kind of like these notations in red because they're just easy to follow and quick to write. Next slide. A matrix is in reduced row echelon RRE form if it meets the following conditions. So the leading entry of each row, if there is one, is a 1. Now, not every row has leading entries. Remember, a leading entry is the first non-zero number, and if a row has all zeros, then it won't have a leading entry. But if there is a leading entry, it must be 1. 2, the leading ones appear further to the right from row to row. 3, any rows of all zeros are at the bottom of the matrix. And 4, all other entries in a column with a leading 1 are 0. Okay, so we're going to meet all 4 of these conditions, or at least we're going to use row operations on this matrix to put this matrix in RRE form. In other words, we're going to row reduce it, and we're going to get it to the point where all 4 of these conditions are satisfied. All right, the first thing you want to do is, if there is a 1 in the first column, then you want to just get it to the top position by doing a row interchange. But notice there isn't any 1s in the first column. So we can make a 1, though, in the first column in any position by simply multiplying a row by the reciprocal of the leading entry. So if you have a negative 5 here and you want that to be 1, then I would just multiply everything in this row by negative 1/5. This is one option. However, that's going to cause fractions here and here, which isn't necessarily desirable. If you can avoid fractions and achieve your goals, then great, because working with whole numbers in your head is a little bit easier, or integers is easier than working with fractions sometimes. I noticed that I could get a 1 in this position here rather easily by multiplying the second row by 1/5. And that will not cause any fractions to surface. So that's what I'm going to do. So I'm going to multiply row 2 by 1/5. And let's see what this creates. So the top row is going to be -5, -4, 12. Multiply the second row by 1/5. That's going to be a 1, and then a 2, and then a 0. And then a 0 to -4. Now I want to get that 1 in the top position. So I'm going to do a row interchange next. So I'm going to interchange rows 2 and 1. The first row satisfies this condition. The leading entry is 1. Now, let's look at the fourth condition. All other entries in a column with a leading 1 are 0. So we have a leading 1 in the first column. So this first column has a leading 1 in the top position. So I want below it to both be 0. These both have to become 0. Now the bottom one's already 0, but the -5 needs to be changed. And I'm going to do is use this leading 1, also called a pivot 1, by the way. I'm going to use this leading 1 to 0 out all the entries in the column, all the other entries in the column. And I'm going to use the third row operation to do this. So I'm going to multiply temporarily row 1 by 5, and then add that to row 2 to 0 out this position. And let's see what this produces. Let me go to a new line down here. And let's do some copy paste. And the first row and third row are not intended to change when I do this. So just the second row. And here's where we do the work in our head. So we're going to multiply this 1 by 5. So it turns it into 5, and then add it to -5, and that makes 0. Now we're going to do 2 times 5 is 10, and add that to -4 gives me 6. And then we do 5 times 0 is 0, and then add that to 12, stays 12. Okay, so we've met the first and fourth conditions are so far, well, at least concerning the first row. Notice that the second row, the leading entry is 6, and the third row, the leading entry is 2. Now I could make both of these 1 rather easily right away by doing a row operation of multiplying a row by a non-zero scalar. So in other words, multiply row 2 by 1/6 and multiply row 3 by 1/2. I feel it's safe to do both these row operations at the same time. So we have 1, 2, 0 in the top row. That's not being changed. Then we're going to have 0, 1, 2, and then 0, 1, -2. All right, and this is where we're at now. Now I'm at a position where the first condition is completely met because the leading entry of each row is 1. 1, and these two 1s are both leading entries. Now, the second condition says that leading 1s appear further to the right from row to row. So in the first row, the leading 1 is there. Second row, it's there. But in the third row, it's directly below. We don't want leading 1s to be directly stacked on top of each other. We need them to be further to the right as we go down the matrix. And so, in other words, this leading 1 we want to 0 out. And we're going to use the leading 1 directly above it to do it. Which means I never needed to make that a 1. I could have not done this row operation here. I could have left this as 2, -4, but then 0 out the 2. So there's options, and there's lots of ways to go about doing these kinds of problems. I'm going to go ahead and leave that row operation in there, though. And I'm going to use the third row operation now to use this 1 to make this 1 a 0. So I'm going to multiply row 2 by -1 temporarily and add it to row 3 to produce a new row 3. Okay, so I'm going to copy this matrix. We're producing a new row 3, so let me delete row 3. And let's do the calculations now. So we do -1 times 0 is still 0, and add it to 0. So that's going to stay 0, which is good. We don't want this column to change at all. Now we're going to do -1 times 1, which is -1, and add it to 1, so that zeroes out. And then finally, we're going to do -1 times 2 is -2, and add it to -2. That gives me -4. Okay, so we are getting closer to RRE form. We have these two leading 1s and they're further to the right as we go down. But then now that we have a leading entry that's further to the right, but it's not a 1. So we're going to multiply that bottom row by negative 1/4 next. And that produces a new matrix. And we're going to multiply the entire bottom row by negative 1/4. So that's really just going to make that a positive 1. Okay, now let's check our conditions. The leading entry of each row, if any, is 1. Yes, we have 3 leading 1s there right there. Leading 1s appear further to the right from row to row. Check. There's no leading 1 above another leading 1. Any rows of all zeros are at the bottom. Where there are no rows of all zeros, if there were, we would just do a row interchange and get them to the bottom. And the fourth one, all other entries in a column with a leading 1 are 0. Well, that's not the case here, because here's a leading 1 in this first column. In fact, every column has a leading 1, and we have 2 zeros here, so that's satisfied. The first column is good. The second column, though, has a leading 1 right here, and so we need all the other entries, we need that to be a 0 and this to be a 0. So what we're going to want to do then is do some more row operations. I'm going to do negative 2 times row. I'm going to use this leading 1 right here to zero out any entries in its column that aren't currently 0. So looking at the second column, we want this 2 to be a 0. So I'm going to use this 1 to do it. So I'm going to multiply row 2 by negative 2 and add it backwards up to row 1. And let's see what this produces. Okay, row 1 is targeted for change, so let's erase that. And we do negative 2 times 0. We have to do this row operation to the entire row, by the way. So we do negative 2 times 0, 0, add it to 1, stays 1. Then we do negative 2 times 1 is negative 2, and add that to 2, turns that to 0. And then we do negative 2 times 2 is negative 4, and add it to 0, makes that negative 4. Okay, so the first column is prepped, the second column is prepped. Now we have to look to this third leading 1 and look to its column that it's in, and all the entries in it, all the other entries in that row with that leading 1, or sorry, in that column with that leading 1 must be 0. So we need both these to be 0 next. So I'm going to use the third row operation again. I'm going to multiply bottom row by negative 2 and add it backwards up to the second row to make that 2 a 0. And we are using this leading 1 to do this. And then also in the same step, I'm going to do a second row operation, multiply row 3 by 4 and add it back up to row 1 to make that a 0 up there as well. So this should be our final step here to get RRE form. Only row 3 is being unaffected by this change. So I'm going to write row 3 in first to make sure it's the same. Now let's create the new row 2. We do negative 2 times 0 and add to 0. Stays 0. We do negative 2 times 0, add to 1. That's going to stay 1. We do negative 2 times 1 and then add to 2. That's going to give us the 0 we want right there. Now let's do the second row operation, doing the 4 times row 3 and adding it to row 1. 4 times 0 and add to 1. Stays 1. 4 times 0 and add to 0. Stays 0. And then finally, 4 times 1 and add it to negative 4 gives me a 0 up there. Okay, now let's investigate all 4 conditions. The leading entry of each row is 1. Check. Those 3 ones there are all leading entries, and they're all 1s. Leading 1s appear further to the right from row to row. Check. So we sort of create this descending staircase of 1s, if you will. We have to go further to the right every time we look at a new leading 1 going down the matrix. Any rows of all zeros are at the bottom. Well, there are no, so condition 3 really just doesn't apply here because there are no rows of all zeros. And then 4, all other entries in a column with a leading 1 are 0. And since every column has a leading 1, there's a leading 1, we had to make zeros in all the other entries of that column. Here's another column with a leading 1, so we had to make zeros be here and here, which is good. Then here's another leading 1, so we need zeros here and here. So all 4 conditions are met. This is said to be in RRE form. Next one, adding and subtracting matrices is done by adding and or subtracting the corresponding entries. And it is only possible if the 2 matrices have the same dimensions. So you want to add a 2 by 3 with a 4 by 3. Make sure they have the same dimensions. And so this is a 2 by 2 matrix, and this is also a 2 by 2 matrix. So if they're the same dimensions, you can add them together, and you just add them by adding corresponding entries. So you do 6 plus -3. And 6 plus -3 is 3. And then we do 0 plus 7. That stays 7. It's like you're just overlapping the two matrices and adding the corresponding entries. And then 5 plus -1 is 4. And then finally, -2 plus 1, adding those entries, is -1. Okay, subtracting is similar. You can subtract them if they're the same dimensions. So we have a 2 by 2 and subtracting another 2 by 2, so that's okay. And we just subtract corresponding entries. So we do 6 minus -3. Make sure the negative distributes. 6 minus -3. So it's going to be 6 plus 3, and we get a 9 in the top, in the 1, 1 position. First row, first column. And then we do 0 minus 7, and we get -7. Now looking at the 2, 1 position, we do 5 minus -1. 5 minus -1. That's going to be 5 plus 1. It gives me a 6. And then finally, the last position, the 2, 2 position, we do -2 minus 1. That gives me -3. Okay. Now to perform scalar matrix multiplication, multiply each entry of the matrix by the scalar. So when you put a scalar, which is, remember, a 1 by 1 matrix or just a number, times any matrix, you just distribute that scalar to every entry. And so this is as simple as getting -18, which is 6 times -3, -3 times 0 is 0, -3 times 5 is -15, and -3 times -2 is 6. Now, matrix-matrix multiplication is a little bit trickier, and you're not able to multiply any two matrices together. A certain condition has to be met. And that condition is as follows. Note that A times B is only possible if the number of columns of A equals the number of rows of B. So let's look at the matrix out on the left. Notice A times B, and we're putting A on the left. By the way, matrix multiplication is not commutative, so A times B generally is not the same thing as B times A. In fact, A times B might be possible, whereas B times A might not even be possible. So the matrix on the left is 2 by 2. It's 2 rows, 2 columns. And the matrix on the right is 2 rows, 3 columns. Now the number of columns of A, which is the matrix on the left, so the number of columns of the left matrix has to equal the number of rows of the right matrix. In other words, these two middle numbers here have to be the same. So you got to verify these have to be the same. Check. And the result will be the outer numbers. So the result is going to be a 2 by 3 of this matrix multiplication. And here's how it's done. You begin by, you take the first column of the matrix on the right, which is 1, 2. You sort of drag it out of there like a train. It drags it to right there. Turn it sideways into a row and drag it out there above the other row. And then you drop these numbers onto these entries, multiply the ones that correspond, and then add the results. So it looks something like times plus times. So we do 6 times 1 plus 0 times 2. So we have the 1 and the 2 there. And we do this mostly in our heads. We do 1 times 6 plus 2 times 0. So that's 6 plus 2. And that gives me 6. Sorry. 6 times 1 is 6 plus 2 times 0. So we have 6 plus 0. We get 6. Then you take this 1, 2, and you drop it down to these entries and do the same thing. We do 5 times 1 plus 2 times -2. So in other words, we get 5 times 1 is 5, 2 times -2 is 4, and add 5 and -4, and we get positive 1. So the first column of the product matrix is found by using the first column of the matrix that's on the right. And then you repeat this from column to column. So now I grab the second column and drag it out like a train. So put a 3 and a 4 here, or at least imagine that happening. And then that 3 and 4 drop on these entries. You multiply the corresponding entries. So we're going to do 6 times 3 plus 0 times 4. Well, 0 times 4 is 0. So we just have to do 6 times 3 and we get 18. And then we take this 3, 4 and drop it down on these entries and do the same thing. So we do 3 times 5 is 15 minus 2 times 4. So we're going to do 15 minus 8. When I combine these, 15 minus 8 is 7. And then finally, we're going to create the third column of our product matrix by using the third column of the matrix on the right. So drag out that -1 and 0. And then drop it on these entries, multiply corresponding entries and add. So we have -6 plus 0, so we get -6 to begin. And then we drop that down here. -1 times 5 is -5 plus 0, so we just get -5. And this is our product matrix. And notice, in fact, it is, as expected, it is 2 by 3. So in this case, if I were to switch these around, so let's call this first matrix A and the second matrix here B. So if I tried to do B times A, let's look at their dimensions. B is 2 by 3 and A is 2 by 2. So this matrix, this product is not possible because these numbers don't match. So not the same, thus the product not possible. At least the product as defined this way. And you can kind of see why that would be, right? If you were to put the matrix A on the right, you wouldn't be able to repeat this process. For example, let's put B here. We have 1, 3, -1, 2, 4, 0. And let's put matrix A over here, which was 6, 0, 5, -2. If I take this 6, 5 and bring it up and drag it over here to 6, 5, notice there's not enough entries to go around. Right? Because this matrix here has 3 columns, we need 3 rows here to have enough numbers. So the way we've defined this multiplication is just not possible if we try to do it in the other order. So in general, matrix multiplication is not commutative. A times B is not the same thing as B times A, which isn't to say that that never happens to be the case. It just says in general that's not true. But there are some matrices where A times B will be the same thing as B times A. Just generally not true. Okay, now looking at the next slide. A matrix is square if the number of rows equals the number of columns. The main diagonal of a square matrix consists of all entries of the form A sub I. So in other words, A11, A22, A33, A44, etc., they form what's called the main diagonal. A square matrix is diagonal if all entries not on the main diagonal are 0. And an identity matrix is a diagonal matrix with 1s on the main diagonal. So let's do an example here just off on the side. There's a 3 by 3 square matrix. The main diagonal is the 1, 5, 9. However, this is not a diagonal matrix because the other entries, the ones that are not currently highlighted, are non-zero. But if you make all those entries 0, so zeros everywhere else not on the main diagonal, then we have what's called a diagonal matrix. And furthermore, if the main diagonal is only 1s, then we have what's called an identity matrix. Okay. Now let's do some multiplication with identity matrices. Here we have a 2 by 2. It's being multiplied by another 2 by 2. This is possible because these numbers here match, and the result will be the outer numbers. So the result will also be a 2 by 2. So I'm expecting that to happen. I'm going to grab the 1, 0 here, the first column of the matrix on the right, drag it over here, and then drop it on these entries. So you get 1 times 6, 0 times 0, 1 times 5, 0 times -2. So we're just going to get 6 and 5 as the first column. Now let's take the second column, 0, 1, drag it out over here, 0, 1, and drop them down. 0 times 6 and 1 times, that's going to 0 everything out. Then we do 0 times 5 is 0, and 1 times -2 is -2. Combine those, we get -2. So we get 0, -2. Notice that in this case, I did some matrix A, and I multiplied it by a 2 by 2 identity matrix. Sometimes that's written as I sub 2 to indicate it's identity matrix that's 2 by 2, but You can leave off the subscript if it's obvious that it's a 2 by 2 from another context. But notice that when you multiply by the identity matrix, we got A right back. This is why we call it the identity matrix. It's kind of like 1 is the identity. In fact, it's very much the same idea that 1 is the identity of scalar multiplication. Right? 1 times anything won't change it. Well, the identity matrix times a matrix won't change it. Let's look at if we put the identity matrix on the left. Remember we said that matrix multiplication is not commutative in general. But here's a 2 by 2 identity matrix, and here's a 2 by 2 other matrix. This matrix multiplication is possible because these outer numbers are the same, and the inner numbers are the same, and the outer numbers will be the result. So this will produce a 2 by 2 as well. And this time we're doing an identity matrix times some other matrix, and let's see what we get. You can probably guess what we're going to get. Okay, let's begin by taking the 6, 5, and dropping it onto this first row. So we do 6 times 1 is 6, plus 5 times 0 is 0. So we just get 6 plus 0, which is 6. And then here we're going to get 6 times 0 is 0, add 5 and 1. So 6 times 0 is 0, 5 times 1 is 5, and then add those, we're going to get 5. So we got 6 and then 5. Now we're going to grab the 0, negative 2 and do the same thing. 0 and negative 2. Right. Oops, let me grab those. Okay. So drop them on these entries, 0 times 1 and negative 2 times 0. And we're going to get 0 plus 0. We're going to get 0 again. Then we do 0 times 0 and negative 2 times 1 and add those results, and we just get negative 2. So we got 0 and then negative 2. And notice that's the exact same thing as the matrix A. So the identity matrix does commute with another matrix that's square. A times I is the same thing as I times A, and you get A in both cases. Now the next section. Suppose the product of two equally sized square matrices is the identity matrix. Then the two matrices are said to be inverses of each other. So that's what's going to happen here in this case. Let's do matrix multiplication. Let's take this. Let's first analyze the dimensions. It's always good to think about that. This is a 2 by 2, and this is another 2 by 2. So once again, I'm expecting a 2 by 2 result. I'm going to grab the 2, negative 5, drag them out over here, 2, negative 5. Drop them down and combine. So we do 2 times 3 is 6, and negative 5 times 1 is negative 5, and combine those, we get 1. Drop it down to here. 2 times 5 is 10, and then add it to negative 10, so we get 0. So we got 1, 0 is the first column. Now we're going to take this negative 1 and 3, drag it out over here, negative 1 and 3, and drop them down onto the rows. Negative 1 times 3 is negative 3, plus 3, we get 0. And then drop this down to here. We have negative 5 plus 6. That's going to be 1. So notice, when I multiply the two matrices, I got the identity matrix as a result. So that means that if you call this matrix A, then this one here is said to be the inverse. And you can write it as A with a negative 1 like that. So an inverse matrix is a matrix that, the inverse of a matrix A is another matrix, so that when you do A times that inverse, you get the identity matrix. These ones will also commute. When this happens, I'm going to leave this to you to verify, but if you switch the order of this multiplication and then redo it, you will also get I. So a matrix times its inverse is they commute with each other. Or if you're to call this matrix here B, if ever you get A times B is equal to I, and A and B are the square equally sized, then we can say that B is equal to A inverse, or we can say that A is equal to B inverse. Right, this negative 1 power on a matrix suggests this idea that we have an inverse matrix. When you see the negative 1 power on a matrix, do not do this. In fact, we have no meaning. Right, this is a bad thing. We have no meaning for division by a matrix, just matrix multiplication. You can make a similar argument for numbers, by the way. You could say dividing by 2, there's no such thing as division by a number. It's multiplying by an inverse. So when I have 6 and I say I want to divide by 2, we can say, no division, but you can do 6 times the inverse of 2, which is a half. So you could construe all division as multiplication and make the argument that we never have division of numbers. If it exists, the inverse of the square matrix A is found by row reducing AI to IA inverse. Okay, what that means is, let's call this matrix here A, and let's say we didn't know the inverse, which is the B here, which is given. We're going to show you how to find that inverse. So you begin by writing A next to an equally sized identity matrix. So we begin by going 3, 1, 5, 2. Sometimes a little bar is put here to separate the two. You don't have to put it, and then you put the identity matrix of the same size right next to it. So this is what we mean by doing this A bar I. And then we're going to row reduce this so that the left side becomes the identity. All right, so I need to get a 1 in one of these two positions. But if I multiply the top row by a third, that'll give me a 1 here, but it'll make a fraction, and I don't want that. If I multiply the bottom row by a fifth to make a 1 here, that's going to create fractions over here, and I don't want that. So if there's ever a way to avoid fractions, do it. Now I see a way that we can avoid a fraction. Because if I double this row, this will make this a 6, and 6 is 1 unit away from 5, which means I'll be able to do a combination of row operations to accomplish this. I'm going to begin by just doubling the top row. Okay, so it's going to produce a new double matrix, and we do this to the entire extended matrix here. All right, so we're going to double the top row, all of it. So we're going to get 6, 2, 2, 0. Now that I have a 6 above a 5, I could do -1 times 5 and add it backwards up to here to make a 1 there. And this will avoid any fractions surfacing, at least for the time being. It might be impossible to avoid fractions entirely, but you can certainly do you can avoid a lot of them that aren't necessary. So I'm going to do -1 times the bottom row and add it to the first row. So let's copy all that. Let's paste that right there. And this is intended to change the first row. Okay, here we go. -1 times 5 is -5. Add it to 6 makes a 1. And that's the 1 I want in that top left position. 2 times -1 is -2. Add to 2 makes a 0. Well, that's convenient. Gives us a 0 right there right away. -1 times 0 is 0. Add it to 2, so that's going to stay a 2 right there. And then -1 times 1 is -1, and add that to 0 is -1. All right, so we got a leading 1 right here. Now we need this to be a 0 below it. So I'm going to do now -5 times row 1, and add that back down to row 2. Let's copy and paste that down here. This time we're going to be changing row 2, so let me erase row 2. And let's do the mental work. 1 times -5 and add to 5. That gives us a 0 right where we want it, right there. 0 times -5, which is 0 still, add to 2. So we get 2 still in that position. And then we have -5 times 2 is -10. And -10, that we're going to now add that to this 0 here, is still -10. And then finally, -1 times -5 is 5. Add it to that 1 there, gives me a 6. Okay, so this is close to being the identity matrix. There's only one step left to making the left side look like the identity, and that is we're going to change this to a 1 by multiplying the bottom row by a half. All right, so we're going to get the same matrix we had before, but the bottom row, everything's going to be half of what it used to be. So I need to change these 3 digits. And half of 2 is 1, half of -10 is -5, and half of 6 is 3. So once you get to this phase, right, notice we began with a structure that was A/I. I effectively row reduced this, producing I/a new matrix. And that new matrix is the inverse of the original matrix. All right, so this tells me that let's call it this way, A inverse is equal to this 2 by 2 that's sitting right here. And there's our inverse matrix. Notice that is exactly what we had up here that we called B. All right, next slide. The determinant of a square matrix is a scalar found in the following ways. Note that a square matrix is invertible, that it has an inverse, if and only if its determinant is non-zero. And I should mention back up here that not every square matrix has an inverse. If ever you try to find the inverse of a square matrix and you're unable to produce the identity right here, then that's an indication that the original matrix was not invertible. A matrix that is not invertible, by the way, is called singular as well. I don't have that written down here, but you'll see that word singular. So if a matrix is invertible, that means it is non-singular. Because a singular matrix is one that's not invertible. So singular means not invertible, non-singular means invertible. And we're going to note that square matrices are only invertible if and only if its determinant is non-zero. So to find the determinant of a square matrix, you just put the word det in front of the matrix, or you put the matrix in what appear to be absolute value bars. So notice that these don't have the little tails on the bars here. They're not brackets. If you put a matrix inside what appear to be absolute value bars, then that's an indication that you're trying to find its determinant. Now, to find the determinant of a 2 by 2 matrix, you do the following. You multiply these entries here, and then get a product, and then you subtract the product of these entries. We're going to multiply those two entries here and keep the sign. Then we're going to multiply these entries and change the sign and then combine, or in other words, subtract that red product. So here's what it looks like. We do -2 times 3, which is just -6, and keep the sign. That's what this plus means. Don't alter the sign. It doesn't mean make it positive. It means don't alter the sign. And then we do 5 times 4, which is 20, but change the sign. So we get -20. So we get -6 minus 20 is -26. This is the scalar. It's a 1 by 1 matrix that is said to be the determinant of this 2 by 2 matrix. And notice that this determinant is non-zero. That means that the 2 by 2 has an inverse. In other words, it's non-singular. Non-zero means non-singulars. That means invertible. Not invertible means singular, means 0 for the determinant. Now let's do a 3 by 3. Now once we go larger than 2 by 2s, we do what's called cofactor expansion. What you want to do for cofactor expansion is identify any row or column that has the most zeros. This will just keep your calculations a little bit faster. So there's only one 0 in this matrix. It's in row 1. It's also in column 2. So you can pick either row 1 or column 2. And we're going to do something called a cofactor expansion along that row or column. Let's pick column or row 1. And what I'm going to do here is I'm actually going to copy this. See if I can copy all that and paste an image. Okay, we're going to expand along the first row. There's a matrix of signs that's underlining this that has the following signs. Top left position is always the positive sign, and then you just alternate like a checkered board. Like if that's positive sign, that's negative, that's positive, and then negative, positive, negative, positive, negative, positive. These signs here form a like checkerboard of signs with the top left corner positive, and they overlap these numbers here. Now I only have to worry about the top row, so I don't care about these. Let me delete these. I'm doing an expansion along the top row. So keep those signs in mind as we do the following. Write it this way. We focus on the 2. We put that plus sign in front of it, and then we cross out the corresponding row and column. And then the determinant is calculated by doing that positive 2 times the determinant of this 2 by 2 matrix that's not crossed out. So times the determinant of 2, 4, -1, 1. And then we repeat this process as we move along the top row. So I'm going to make this more dynamic. Let me just delete a bunch of this stuff here. This will save me some space too. I will put this plus here because we have the matrix of signs plus, minus, plus. And we're expanding along that first row. So then we shift our focus to the next entry in that row and cross out everything else in the row and column. So we have a -0 there. Let's put the orange minus there. 0 is being focused on, so 0 times, and then we do a determinant of the 2 by 2 matrix, submatrix that's not crossed out. Right, so that's these two entries and these two entries. We make a 2 by 2 matrix out of it. But it really don't matter what this determinant is because we're going to multiply it by 0. So that's why expanding along a column or row that has zeros in it will just speed up your calculation because you won't have to bother with this middle piece. And then we shift our focus to that last entry, which is a 3. Cross out everything in its row and column and see what's left is a 2 by 2. And we have a positive 3 with the orange plus sign. 3 is what we're focusing on, and then times it by the 2 by 2 determinant that's uncrossed out currently. If I had expanded along this column, then my matrix of signs would have been a minus plus minus. Right, top left corner is always plus. And we have done an expansion along there. So I first would have crossed out the 0 with its row and column. So looking at that 2 by 2 is negative 3, 1, 4, 1. Then I would have crossed out the 2, and the 2 by 2 that's not crossed out, right, is this 2, this 3, this 1, and this 1. And then I would have focused on that negative 1 at the bottom, crossed out those, and then focused on the 2 by 2 that's not crossed out. So that's how I would have done it if I had done cofactor expansion along the second column. But instead, I did it along the first row. So that was plus, minus, plus. Okay, now we just have a bunch of 2 by 2s to calculate. So we have a positive 2. Now we're going to do a 2 times 1 is 2, minus a negative 4, and 2 minus negative 4 is 6. So there's going to be a 6 there. Minus is 0. We don't care about that. Middle piece will 0 out. Plus 3 times, and we do negative 3 times negative 1 is 3. And then we go minus 2. 3 minus 2 is 1. So we get 12 plus 3 in the end, and we get 15 as our determinant. Notice that this determinant is also non-zero, meaning that this 3 by 3 matrix that's represented here has an inverse. And then finally, a 4 by 4 matrix. Again, look for a column or row. I'm not going to actually finish this one for time's sake, but I'm just going to get it started. Identify a column or row that has the most zeros, and I see the second column has the most zeros. Get your matrix of signs in there. So this would be plus, that would be minus, and then going down that, and I don't really care about that first plus. So I'm going to expand along this. Let's highlight those, the rows and or columns that I'm using to expand along. Okay, so now I'm going to begin by crossing out the negative 1. And negative 1 is crossed out, so we have negative 1, and it's negative because of the orange. The orange is the negative part. Multiply it by a 3 by 3 determinant of a 3 by 3 matrix that's not crossed out. So negative 2, 4, 5 is the first column. Second column is 2, 1, 1, and then we have 1, 0, 5. Now to find this 3 by 3 determinant, you're going to have to do cofactor expansion as well. So there's you have to do, effectively you have to repeat this task up here for each of these 3 by 3 determinants you get. So it does get more and more complicated the larger these matrices get. Now I'm going to move down this column and cross out the 0. But that's going to zero everything out, so I'm just going to put a nice plus 0 there and not write anything else. Then we keep marching down, and now I cross out the negative 2. The negative is from the orange, so I'm going to put minus 2 times, and then a 3 by 3 that's not crossed out. So writing everything that's not crossed out. So you have the first column is 3, negative 2, negative 5. Second column is 0, 2, 1. And third column is 3, 1, 5. Okay, and now we do crossing out the last entry in that column, which is a 0 again, so it's just going to 0 everything. Technically, it's a positive 0 again, but whatever, it doesn't matter. That's going to be 0 out. So to finish this problem, you have a 3 by 3 determinant to find still, and another 3 by 3 determinant to find, where you'd have to repeat this process to get each of those. And then you can complete this calculation. So I'm just going to put some dot dots. I'll let you do that on your own time. And then you can reach for a determinant calculator. There's lots of online matrix calculators that you can find for free and test your work here and see if you get the right answers. Now, certain systems of linear equations can be solved in 3 basic ways shown below. So this is a system of 2 equations. They're linear equations because it's x to the first and y to the first. And we have 2 equations, 2 unknowns. one way to do this is without using any matrices at all. You can just do substitution and or elimination. And for example, if I do substitution, I would maybe solve this first equation for y and then substitute it in for this y and then solve for x. Or I can do elimination, which is what I'm going to do here. I can multiply, let's write down, do substitution or elimination are your options here. As one method. So just manipulating the equations, in other words. And let's do an example of elimination. So I'm going to multiply the top equation by -2. So we have negative 6x minus 2y equals -8. I'm going to leave the second equation the same. And I'm prepping this so that when I add the two equations together, the y's eliminate. So add these together, you get negative x, the y's eliminate, and over here you get -9. And now, so that, therefore x is 9. Then you can plug 9 into either equation, doesn't matter which one, and solve for y. Let's plug it into the first equation, the one that's right there. So we know that 3 times x, which is 3 times 9, plus y is equal to 4. Therefore, 3 times 9 is 27. Subtract that from 4, so y therefore is -23. And so we have a solution that's 9, -23. So this is one way to do this, substitution and or elimination. No matrices involved. Second way, let's call this the first way. Second way is to create what's called an augmented matrix. So we're going to make sure the x's are lined up and the y's are lined up and then the constants are lined up. And then just write all those numbers down and make a 2x3 matrix called an augmented matrix. And we're going to say row reduce an augmented matrix. This is the method. So to create the augmented matrix, the x's are 3 and 5, the x coefficients I should say. The y coefficients are 1 and 2. And then on the other side of the equal sign is the constants 4 and -1. So we create this 2x3 matrix. Sometimes people like to put a little line right here to represent where the equal sign was, which is, I recommend doing, doesn't hurt. And then I just want to put this 2x3 matrix into reduced row echelon form. All right, so let's do this a few steps. I want up here to be a 1, so I'm going to make that a 6 first. You notice the strategy to avoid fractions. So I'm going to begin by doubling the top row. Okay, so doubling the top row gives me a 6, then a 2, and then an 8. Now I'm going to do -1 times the bottom row and add it back up to the first row. We're changing the first row now, so those are all gone. And we have -1 times 5 and add it to 6. That gives me a 1 up there. -1 times 2, add to 2, gives me a 0. -1 times 1, add to 8, gives me a 9. And now I'm going to get a 0 beneath this one here. So I'm going to do now -5 times row 1 and add that down to row 2. Okay, so that gives us we do -5 times 1 is -5, add it to 5, gives me a 0. -5 times 0 is 0, add it to 2, stays 2. And -5 times 9 is -45, and add it to -1 is -46. And we're almost in reduced row echelon form. We have a 1, we need this to be a 1, and we need zeros in those columns, check, check. We just need that to be 1, and we're good. So we're one step away, multiply the bottom row by 1/2, and this should finish our reduced row echelon form, giving us 0, 1, -23. Now we just convert these back to equations. Remember that this is the coefficient of x, this is the coefficient of y, and then you add them together. So in other words, x plus 0y, so just x, equals 9. So convert to equations again, gives me x equals 9, and the bottom one would read y equals -23. Right, confirming a solution we got over here. So this is row reducing an augmented matrix. And then the third method is to use the inverse, to write this system in matrix form and then use the inverse of a coefficient matrix. I'll show you what I mean by that. So I'm going to take the coefficients of x and y and write them as a separate matrix. So we have 3, 1, and then 5, 2. Then multiply by the column matrix of the variables x and y and set that equal to the column matrix of the constants. Now notice this matrix equation makes sense because, first of all, this is a 2 by 2, this is a 2 by 1, and this is a 2 by 1. So these inner numbers match, so the multiplication is possible, and the outer numbers will be the result, 2 by 1, which is exactly what we see here. And you would do this multiplication by taking the xy, dragging it up here, x and y, and then dropping them down onto the 1 and 3, or 3 and 1, and then multiplying and adding. So this would read 3x plus 1y, in other words, 3x plus y. And this would read 5x plus 2y. And that would be equal to these numbers respectively over here, 4 and negative 1. So we're just expressing this system of equations as a single matrix equation. It's a matrix times a column vector of variables equals a column vector of numbers. And we can call this the matrix A, sometimes a capital X, or putting a bar above it, or making it bold, or making it a formal capital X like that, just whatever makes it stand out so it stands for a vector. We're going to see some vector notations that if you just put a little single arrow above a symbol like this, it means it represents a vector. Let's go ahead and go with that notation, and is equal to a vector B, we'll call it. So we have a matrix A times a vector X, and the vector X is a column vector of variables, so x, y in this case. If it was 3 by 1, it'd be x, y, z. If it's 4 by 1, it might be x, y, z, w or something, is equal to another column vector. And one way to solve this, right, if you have a matrix A times a column vector of variables is equal to a column vector of numbers, and A is square, and it's invertible, then if you multiply both sides on the left by A inverse, and I have to say on the left, so I have to put A inverse on the left of each side. Multiply A inverse and A together first, that makes the identity matrix. And the identity matrix times anything doesn't change it, so we have just the x vector. And so this gives us a way to solve for the x vector using an inverse matrix. Now, I've already found the inverse of this matrix. You might recall it was up above. A few slides back, it was here. All right, we found this inverse. I'm just going to copy it. Here is the inverse. If you don't know the inverse already, then you're going to have to recalculate it. So we get that x, the vector x, is equal to the inverse matrix times the vector b. And the vector b was this 4, negative 1. And of course, the vector x stands for xy. And now we just have to do this matrix multiplication to get our answer. So I can take this 4, negative 1, right, bring it up here, and then drop these entries down, multiply corresponding entries and add. So we get 4 times 2 is 8, plus 1, so we get 9. And then we take the 4, negative 1, drop it down here. We get negative 20 minus 3, we get negative 23. Now this third method is only possible if the system is square. In other words, if in matrix form, the coefficient matrix here, A, is square. And A has to have an inverse, because not every square matrix has an inverse. It'll only have an inverse if its determinant is non-zero. If the determinant of a square matrix is 0, then that square matrix will not have an inverse, and this third method will not be applicable. Substitution and elimination get complicated when there's lots of variables and lots of equations. The way that's going to consistently give the right answer, or an answer that is valid, is really doing method 2, row reducing an augmented matrix, because this will be helpful in all those cases where maybe the coefficient matrix isn't square or doesn't have an inverse, or if there's lots of variables involved. And this method over here gets quite complicated if there's lots of variables involved. And so often method 2 will be the go-to method. In fact, I'm going to use method 2 on our last slide. A system of linear equations can have one, none, or infinitely many solutions. Solve each system below presented as augmented matrices. So this is already an augmented matrix. I'm going to put the vertical line here to represent where the equal sign was. Keep in mind then that the first column represents the x coefficients, y coefficients, z coefficients, and equal sign, and then our constants on this side. So this first line would read x minus 2y plus 0 is equal to 4, etc. Now I'm going to solve the system by putting this augmented matrix in reduced row echelon form. Let's begin by doing, noticing the first column already has a 1 in the right position, but I want this 2 to be a 0. So I'm going to multiply the first row by -2 temporarily and add it to the second row to create a new second row. And this will yield, first row will be the same, so 1, -2, 0, and 4. Third row will be the same, so 0, 1, 2, -2. It's just the second row we're changing. And we do -2 times 1 is -2, add to 2 makes a 0. -2 times -2 is 4, add to -1 is 3. -2 times 0 is 0, add to 6 is 6. And -2 times 4 is -8, add to 2 is -6. At this point, I already have a 1 right here, so I'm going to do a row interchange between these two rows. That gets me a leading 1 in this position right here. I'm going to use that leading 1 now to make this a 0 below, and this is 0 above. So I'm going to do row operation 3 twice. I'm going to double row 2 and add that to row 1, double it temporarily, and then I'm going to multiply row 2 by -3 temporarily and then add it to the third row. Okay, doing the first row operation, double 0 and add it to 1, stays 1. Double 1, add it to -2, becomes 0. Double 2 and add it to 0, gives me a 4 here. And double -2 and add to 4 gives me a 0. Now multiplying by -3, row 2. -3 times row 2, add it to row 3. We're going to do -3 times 0 and add to 0, it stays 0. -3 times 1 and add to 3 will become 0. -3 times 2 is -6, add to 6 becomes 0. And -3 times -2 is 6, and add to -6 also makes 0. So this gives me a row of zeros all at the bottom, and this is in reduced row echelon form at this point. Reduced row echelon form. Because we have leading ones that are, or leading entries that are 1s. In the columns with leading 1s, all the entries other than the leading ones themselves are 0, and any row of zeros is at the bottom, and leading 1s appear further to the right as you go down the matrix. So this is reduced row echelon form. Now keep in mind that we have the first column represents x coefficient, then y and z coefficient, and then we have this equal sign right here that I've not been writing. And the leading ones, I'm going to highlight them. They're here and here. They are in the x and y column. Any column that corresponds to the coefficients of a certain variable that does not have a leading 1 is going to represent what we call a free variable. So we're going to say that z is free. Z can be whatever number we want. And then I'm going to translate row 1 back into an equation. Row 1 would read x plus 4z is equal to 0. And row 2 would read y plus 2z is equal to -2. Now if you solve each of these for x and y, you're going to create a system of a solution to this system of equations. So x is going to be equal to -4z. Y is going to be equal to -2 minus 2z. And z is free. So you can just write z as free again. And this would be our answer. This gives us infinitely many solutions because z can be whatever number you want. For example, if z is 10, you can choose it to be 10. But then change both these z's to 10 and do these calculations, and that will tell you what x and y have to be at the same time. And then you let z be a different number, etc., and you get infinitely many solutions. Now, other ways of expressing this, you're going to see the homework likes to give z the value of s. And I don't like s's because they look like 5s, and then you change these z's to s's as well. But you can see why this might be problematic. If you're going to insist on going with another letter, oops, let's put that 2 back. Maybe a would be an easier one to write. Of course, you don't have to do any of this. You could just say, like what we did before, just leave these z's and cross your z's so they don't look like 2s, and say down here that z is free. Z could be any real number. Okay, and this next one, The only difference between this augmented matrix and this one over here is the bottom right position. This is the A34 position, third row, fourth column. It's a positive 2 instead of a negative 2. So we can get this one started in a very similar way. So I'm going to copy this information here and just paste it over here. And the only difference is that this will be a positive 2 down there below. I'm going to do the row interchange as well, again, so let's copy some more. Only difference is that will be a positive 2. And I'm going to continue with our next two row operations as indicated here. And let's see what we get as a result. So 2 times the middle row and add that back up to the top row. Well, the middle row is not going to change. Let me write that in here first. And 2 times 0 add to 1 is 1 still. 2 times 1 add to negative 2 goes to 0. 2 times 2 is 4. Add to 0 becomes a 4. And 2 times 2 is 4. And add to 4 gives me an 8 now here. Now let's do the negative 3 times row 2 added to row 3. So negative 3 times 0 is 0. Add to 0 stays 0. Negative 3 times 1 is negative 3. Add to 3 becomes 0. Negative 3 times 2 is negative 6. Add to 6 becomes 0. And negative 3 times 2 is negative 6. Add to negative 6 becomes negative 12. Remember there's an equal sign sitting right here. And if you're trying to convert row 3 into an equation, notice what it would read. 0x plus 0y plus 0z is equal to negative 12. In other words, it would read 0 equals negative 12, which is false. And so we say that this system is inconsistent. And by inconsistent, we just means that it has no solution. And you don't necessarily need to go all the way to RRE form to make this conclusion. If ever in this process of trying to get to RRE form, you wind up with a row of all zeros except for the last entry, then this would communicate that 0 is equal to something that's not 0, and that's a problem. That's going to be an indication that you can just stop and that the system is inconsistent. Now over here we had a row of all zeros, and that's not a problem because that would communicate 0 is equal to 0. So that's a non-issue, but this is an issue of all zeros, an equal sign, and then a non-zero. And that concludes our review of matrices.